Today's lesson adds some detail to many of the concepts that hopefully you're already familiar with or becoming familiar with. And so here's a series of questions that are strictly tied to the reading from your textbook. And so I would encourage you to read section 4.8, 4.9, and 4.13 and 4.14 before starting today's lesson, and you'll find that the questions and the answers hopefully make a lot more sense. This first question asks us about two different compounds. They are enantiomers of each other. So that means they're stereoisomers that are non-superimposable mirror images. That's the technical definition of an enantiomer, or kind of the working definition of an enantiomer is they are compounds where I've switched all of their chiral centers. And there's only one chiral center in these compounds. So R-carvone and S-carvone. And this has a common name. It would also have a systematic name, but it involves a ketone, and we're not worried about learning ketone systematic names yet. There's only one chiral center. Here it is. And the fact that the R enantiomer rotates light in a negative or a counterclockwise fashion in a polarimeter has nothing at all to do with the R designation. Remember these two ideas. This is experimentally determined, the negative, and the R is simply based on a set of rules that Kahn, Ingold, and Prelog came up with that may or may not match a specific type of optical rotation. Okay, enough of that tangent. Let's get to the question. So this right here is one of the enantiomers, and this is the other enantiomer. And these two molecules, which are very similar, they have exactly the same atoms, connected to exactly the same other atoms, just happen to differ in three-dimensional space. And the fact that they differ in three-dimensional space is noted by our biological system as a different smell. So R-carvone is derived from spearmint leaves and has the characteristic spearmint scent, and S-carvone comes from caraway seed oil. And to be honest, I don't know what caraway seeds smell like, but I do know what spearmint smells like, and I imagine they smell different. That's the point. And the reason that they smell different is because of how they bind to the sensory receptors in your nose. So one of the characteristics of enantiomers is that chemically they are very similar, but biologically they are very different. So consider here a chiral molecule, and then over on the right-hand side I have the enantiomer of that molecule. So you can tell that they're enantiomers because I have switched the green and the purple, and so that represents a switching of all of the chiral centers. There's only one chiral center. When you have a biological receptor, they are often and almost always three-dimensionally specific. And evolution selects for this type of specificity. And so in your nose, or somewhere up there, the molecule S-carvone would bind to a receptor differently than the way R-carvone binds to a receptor. And so whatever the spearmint cascade of neural signals that's kick-started by, let me get this straight, by the R-carvone is the one that spearmint oil is, that cascade of neural signals that tells you spearmint is caused when the molecule binds in a certain three-dimensional fashion to its specific receptor, or to a receptor that preferentially binds it. And then if you try to shove the other enantiomer into that same receptor site, the binding just doesn't match up. They don't have the right intermolecular forces of attraction, be it hydrogen bonds or some type of dispersive force interaction. But the point of this question is to get you to recognize that biologically it matters very, very much which of the two enantiomers you are giving to the biological system, and they can often have very different effects. The reason that this matters to organic chemists is that the bulk of organic chemists, and the majority of them, will ultimately end up working in a synthetic laboratory. And a laboratory that's synthetic is a laboratory where you build molecules. And many of those laboratories, I don't know that it's the majority, but I would guess that it represents a significant percentage, service the pharmaceutical industry. And so as an organic chemist, when we look at various molecules, we are thinking, how do I build that? And I need to build it in a way that it fits into the biological receptor, meaning that I have to build it three-dimensionally specific. And so if we have if we want to build carvone for some reason that there's a large market demand for people smelling spearmint oil and spearmint leaves are not accessible, and we were to build this from scratch, we would need to build the correct chiral center into the compound. And that type of chiral synthesis is very difficult. A better example of this is ibuprofen. So this is a molecule of ibuprofen right here. I have shown you the S enantiomer. There is only one chiral center in ibuprofen. Hopefully you can take a minute and look at the characteristics of chiral carbons. They need to be sp3 hybridized, so that is not. And these 6 carbons inside of this benzene ring are not sp3 hybridized. And then the other sp3 hybridized carbons that we have over here need to have 4 different things attached to them, and they don't. This carbon has 2 hydrogens, this carbon has 2 methyl groups, and these methyl groups have 3 hydrogens. So this is the only carbon that fits the criteria of being a chiral carbon. And when you synthesize ibuprofen as a painkiller, and then you package that into a pill, what happens is only the S enantiomer is able to act in a biological setting as a pain-killing drug. And so if you take 800 milligrams of ibuprofen, and that is a lot, and it can be wonderful if you're in pain, that 800 milligrams is usually only 400 milligrams of active S-ibuprofen. And so you might ask, well, what happens to the R-ibuprofen? And that's an interesting story. With a lot of compounds that are not chiral, that are chiral, for a lot of chiral compounds, there are actually enzymes that exist that are somewhat generic. They're non-specific, and they have a tendency to invert chiral centers. In Chemistry 352, you will start to appreciate that this particular chiral center adjacent to a carbonyl group is especially flexible. And so it can be converted from S to R or from R to S. And so what this means is when you take that pill of ibuprofen, the S-ibuprofen immediately causes the pain deadening sensation, and the R-ibuprofen just kind of hangs out in your circulatory system and is slowly converted into S-ibuprofen as a function of time, or it gets excreted out of the kidneys. And so that creates both an immediate pain-killing effect and a long-lasting pain-killing effect. So it actually works out generally better to give people that enantiomeric mixture of both S and R ibuprofen. And is typically a racemic mixture for reasons that we'll talk about later. It's really easy to synthesize a racemic mixture. That's kind of the default synthesis. And so when people make ibuprofen, they just don't bother to worry about it. You just put both enantiomers in there, and one of them causes immediate pain-killing sensation. And I'm not exactly sure what the mechanism of ibuprofen is, and I imagine a 15-second Google search could help me figure that out. But moving on, what I care about as an organic chemist is the fact that I don't have to clean up that synthesis. I put both S and R in the pill package, ship it off, and the customers actually thank you. So that's the answer to this question. As a side note, one that hopefully is interesting to you, and a little tragic, is the case of thalidomide. So this compound right here also has a single chiral center, and what I've shown here is R-thalidomide. And R-thalidomide was used as an anti-nausea drug, I believe, in the 60s and 70s, plus or minus a couple decades. But it was never approved by the FDA for use in the United States because they felt that inadequate testing was done. And that proved to be very beneficial to people in the United States because while R-thalidomide was effective as an anti-nausea medication and didn't seem to have, to my knowledge, it doesn't have any known side effects, the S-thalidomide causes birth defects. And the problem is you have a drug that stops nausea, and the people that tend to experience nausea are those that are pregnant, especially in the early stages of fetal development. And so they were being prescribed the thalidomide, and I don't know that it was cleaned up. But even if it was, even if you gave a pregnant mother in early stages of fetal development a pure R-thalidomide pill, her body would invert some of those chiral centers because especially notice how, again, that chiral center is adjacent to a carbonyl group. And you'll learn later that that makes them very flexible. And so you would get some S-thalidomide, and that S-thalidomide would pass from the mother through the placenta to the baby, to the growing fetus, and it could stunt the development of the limbs. And it ended up with a lot of children being born with shortened and undeveloped limbs, all four of them. And so instead of having a fully developed arm and a leg, you would have just like a 1-inch kind of stump. And it was just a tragic case. And this was noticed. Europe okayed the use of thalidomide as an anti-nausea medication. And there was actually quite a few people in the United States that were born with that particular thalidomide-caused disease or disorder because their mothers were traveling abroad at the time and sought anti-nausea medication while they were in Europe, and they picked it up, and then the child suffered that deformity. So the point is that from a pharmaceutical perspective, and again, organic chemists often feed into the pharmaceutical industry, and the relationship between organic chemistry and pharmaceuticals is why many of you are probably being asked to take this class as pre-health professionals. But this idea of synthesis that results in a single enantiomer produces often a more potent effect in the medication. But if the other enantiomer is problematic, as in the case of our thalidomide, then unfortunately there are a number of enzymes that kind of operate inside of the human body that will invert these stereocenters. And even if you try to give somebody a pure dosage of one enantiomer, they're going to be exposed to the other enantiomer. It's almost inevitable. Next topic. A happier topic, perhaps. These are called, I've never heard this pronounced, so I'm guessing Trope Isomers. A means without, and trope means turn. And so this is without turning isomers. These are a different type of isomer. And so earlier when I showed you the Venn diagram that referred to stereoisomers as being either enantiomers or diastereomers, there was a little lie in there that there are these things called trope isomers. And the reason that these are hard to classify under normal stereoisomers is that while they are three-dimensionally different, the reason that they're three-dimensionally different is because the molecule, the normal single bond, can't undergo a typical rotation. So these right here represent two benzene rings. That's what they're called. And these benzene rings are decorated with a fairly sterically bulky nitro group and also these carboxylic acid groups. And when you synthesize these, you think about trying to build these things. Let's say that this right here, this single bond between the two benzene rings, is that last bond that you make. And when you put those pieces together, you would expect for this benzene ring to be perpendicular to the first one so that the nitro groups and the carboxylic acid groups can minimize their steric interactions. And when you put those pieces together, it can go together in one or two arrangements. Either a nitro group on top and a nitro group in the back, or a nitro group on bottom and a nitro group on back. And if that single bond were free to undergo rotation, then this nitro group, this bond could rotate, and the nitro group would just come up to the top. And so these two really aren't stereoisomers of each other. They're conformations of each other. They're just different turns of a single bond. The problem, though, is that single bond is not free to undergo rotation. And so while there's no R and S stereochemistry anywhere in the compound, when we put them in a polarimeter, which is the true test of chirality, if something rotates plane polarized light, then it's chiral. And originally we said if it contains a chiral carbon, then it's chiral. And I said there are some exceptions to that. The first exception was the meso compounds that have kind of the dueling or offsetting chiral centers. And this second example here is where you don't have a chiral center, but because of limitations of rotation, you end up with two different three-dimensional conformations. And those are kind of a curiosity, just this trope isomers. And I just pulled this definition right from the glossary of your textbook. It seems to do the trick in terms of defining what trope isomers are. I really should learn how to pronounce that. Next question. Why is it very difficult to separate enantiomers from each other in the laboratory? And I've mentioned that a couple times, that it's really hard. Not only is it hard to synthesize a compound with only one of the chiral, with only one of the enantiomers. So it's really difficult to make S-ibuprofen without having any R-ibuprofen polluting your product. And if you do have any R-ibuprofen in there, it's really hard to separate them. And unfortunately, at this point in the semester, you haven't been exposed, perhaps, to the laboratory because of the nature of the fact that we've shut down laboratories because of COVID-19. So you haven't been exposed to one of the common techniques we use in organic chemistry. So let me stop for a second and explain that particular technique, and then you'll appreciate why this question matters. 10 years from now, when I'm still using this video and COVID-19 is a thing people vaguely remember, they'll be like, why didn't he update the video? We already know what chromatography is, and it's because I don't care. So here's what chromatography looks like. This is a typical ring stand, and this is a glass column. And this column usually is about a foot tall and it can be up to an inch in diameter, but often it's much smaller. And we put some type of liquid permeable plug in the bottom. Actually, fiberglass works really nicely. And then we cover that fiberglass up with sand because fiberglass is uneven and you want to have a nice even surface. The sand and the fiberglass allow liquid to go through, but they keep this and this white column right here. This is what's called silicon dioxide. And it's not, it's a silicon resin. And so it's not silicon dioxide, that's sand. The silicon resin actually is polar. And then you put a little sand on top, and then you start putting your liquid in there. So if you have a liquid that contains, let's say, two different compounds, yellow and brown, and so you put that compound on the top of your chromatography column, and what happens is the liquid starts to push just by gravity. It pushes the yellow and the brown compounds down through the column. They just kind of work their way down there, like tumbling downhill. And what happens generally is one of those compounds will outrun the other compound. And in this diagram right here, the brown compound is moving through the column faster, and the yellow compound is still up here, but over time, and time can be a pain on these. Sometimes it's half hour, sometimes it's 12 hours. Column chromatography is what most chemists spend most of their time looking at. And I'm sure I'm exaggerating, but that was my experience. We do the same thing. I was a biochemist. We can isolate a protein, and then you purify that protein by running it across a column. And unfortunately, not all of the compounds actually have a color, so you can't monitor it with visible light. You have to have some type of detector down here on the bottom that sees in the infrared or the UV-vis spectrum. So this is a little harder than this diagram suggests, but over time, those two compounds will actually start to separate out from each other. And the other complication that we encounter in the real world, especially when you consider biochemistry, is it's not two compounds, it's the entire contents of the cell. And you pop the cells and then just kind of dump the cellular contents across the column, and out comes your lipid bilayer, your DNA, and hopefully eventually you get your protein of interest. Now the question you should ask is, well, why does the brown compound move faster than the yellow? And again, the colors are arbitrary, so there's nothing inherently different between brown and yellow here. But this silica resin right here is generally quite polar. And so the compound that tends to be more polar of the two will work its way through the column more slowly. So the brown compound right here is less polar, and so it doesn't stick to the silica gel as much, so it kind of flows through the column more quickly because it has limited interactions with the column. The yellow compound would be more polar, so it takes longer to work its way down through the column. So this means that most chromatography operates by picking on differences in polarity as the basis of separating out your compounds. And the only reason that two molecules would have identical polarity is if the atoms are connected in an identical fashion. And that's the problem that we encounter with enantiomers. So going back to R-carvone here and S-carvone, the connectivity is the same. All the carbons are connected in the same fashion. And so they really don't have any differences in polarity that column chromatography can take advantage of. So why is it very difficult to separate enantiomers from each other in a laboratory? And that's because our separation techniques exploit differences in physical properties. Polarity is the most common physical property that we use to separate compounds. But boiling point could be one, melting point, any other type of physical property, a property that doesn't require us to chemically change the compound. So our separation techniques exploit differences in physical properties, and enantiomers are, have the same physical characteristics. No, it's not even spelled close to correct. Nope. It's so bad that ChemDraw can't even recognize it. Or sorry, that that autocorrect can't recognize it. I'm going to stop and fix it. Now, if you dutifully wrote down this answer in your lesson, you're going to be mad because this answer is incomplete. Occasionally, our separation techniques will exploit chemical properties as well. And so enantiomers, they don't just have the same physical properties, they have the same physical and chemical properties or characteristics. And this means that they will react chemically the same way. If you set fire to carbone, that's a chemical change, and you measure the heat of combustion, you're going to get the same products and the same heat of combustion when you set fire to its enantiomer. So they have the same chemical and physical properties. And so this makes them very difficult to separate. The only way that they differ is based on their three-dimensional structure. And so the next two questions, look at, well, then how do we do this in the laboratory? Because just because they're difficult to separate doesn't mean they're impossible to separate. And there's a lot of money to be made in chirally pure syntheses. Not every compound is like S and R thalidomide, where they're definitely going to interconvert. And not every compound is like S and R ibuprofen, where it really doesn't matter that you separate them. A lot of compounds, we have to synthesize them in a chirally pure fashion, and that's how we make the money as organic chemists selling pharmaceuticals that only have the right enantiomer. So this is a figure from your textbook, figure 4.12, and we need to explain what's going on here. So explain figure 4.12. That's what we're going to do next. Okay? So what we have here is, this is a flow chart. We have a mixture of two different enantiomers. We don't care which one's R and which one's S because we are pretending that we're doing work in the laboratory. In the laboratory, what we care about is optical rotation, the thing that you can actually measure in the laboratory. And so we start off with a mixture of enantiomers. And that is kind of where we start this problem. So we'll call, let's use a number 1 right here. And we'll indent that a little bit. So you start with a mixture, a racemic mixture. If you remember that word, that means a 50-50 mixture of enantiomers. And then we covalently attach. We're going to make a new chemical bond where we're going to covalently attach a second chiral center to each of the enantiomers. I need to learn to spell. Okay, what that second chiral center does is it changes it from a mixture of enantiomers to a mixture of diastereomers. If you remember, in order to get from one enantiomer to another, I have to change all of my chiral centers. If there is only a single chiral center, then these are enantiomers of each other because I went from positive to minus. When I attach a second chiral center, now you might ask, how do you get the pure second chiral center in the first place? Don't ask. That's a chicken and egg question. Let's pretend that somebody gave it to us. And so we're going to attach that second chiral center to both of these, and now these are no longer enantiomers of each other. They are diastereomers. Diastereomers are where we switch some. So we switched that first chiral center, but we did not switch the second chiral center. So that's our definition of diastereomers, where you switch some, but not all of your chiral centers. And so by covalently attaching the second chiral center to each of the enantiomers, you produce a 50-50 mixture of diastereomers. Now, this isn't given some special name like racemic that I know of, so it's just a 50-50 mixture of diastereomers. And here's the catch. Diastereomers, that seems like the correct spelling. The diastereomers are physically different from each other. They're probably also chemically different in most cases that I'm aware of. They are, But for the sake of this diagram, they are physically different. And generally speaking, they have differences in polarity. So the fact that the enantiomers have the same polarity, so we can't separate those using column chromatography, but the diastereomers now have very subtle differences in their polarity. And often these differences are incredibly small, which means that when you try to run a column using diastereomers, by the time you get down through your 1 foot of your column, maybe they're only separated by 0.5 millimeter instead of having this nice separation that the diagram is trying to show here. So you solve that problem by just making your column really long. And that's common. You can have a 4 to 5 foot column, and that's when it starts to take forever. When the polarity differences are very small, it takes a very long time to separate these things in a column. Because of the time limitations of the laboratory, we usually only give you things to separate in the laboratory that have large enough differences that you can do it in an hour or so. Okay, so diastereomers are physically different, so they can be separated using conventional techniques, meaning the regular techniques that we typically incorporate in the laboratory. And so now we're to the third part of our flow diagram right here. You isolate the separated diastereomers. And so here now we've separated the two one of the diastereomers came off first, and if you know the chemical structure, you can kind of guess based on an understanding of polarity which one might have come off first. But often it doesn't matter. You get one of them off, and then every chemical reaction is reversible. So if it was possible to add this second chiral center, then it should be possible, often with Le Chatelier's principle, to unadd it. You just clip it off. And so then you remove the second chiral center. And that's where we end up here and here. At the end of step 4, you pop that second chiral center off. These are two totally separate molecules, which means you put them across yet another column, 2 separate columns, one for each enantiomer, and voila, you have your purified enantiomer. So this is what's referred to as indirect enantiomeric resolution. Enantiomeric resolution, because we didn't actually separate the enantiomers. In a single step. We separated the diastereomers and then turned them back into the enantiomers. So it's kind of this indirect. We kind of went around to do this, and it takes a lot of time. And again, this is why, as an organic chemist, you're going to make a lot of money if you start synthesizing chiral compounds, or you're going to lose a lot of money if the asking price for those is really small. And that's why hopefully you have somebody who knows business that can do the business stuff while you work in the laboratory and avoid people. Kinetic resolution is another type of separation, and I just pulled this definition from the glossary at the end of your textbook. Kinetic resolution is the separation of enantiomers based on their unequal rates of reaction with a chiral reactant. So this is another example of kind of a chicken and egg issue. Well, how can you ever separate enantiomers if you're going to react them with something chiral? And the answer is you bring in some biochemistry. So enzymes are a typical chiral reactant. I'm trying to think of a good example off the top of my head. I should know some as a biochemist, but yeah, I do. There was an enzyme that I worked with when I was an undergraduate, and we had a chiral compound, and the chiral compound was an epoxide. And if you remember, an epoxide is that 3-membered ring with an oxygen in it. And the epoxide has a lot of angle strain and torsional strain. And there was one enzyme that catalyzed the epoxide popping open. But the enzyme is chirally specific. So we had 2 different enantiomers of that epoxide, and we push it through the enzyme, and the enzyme would pop one of them open very, very quickly in the order of fractions of a second. And then the other one, because it wasn't the right 3-dimensional fit, would pop it open in a time frame of minutes to hours. And so you mix it together with the enzyme, and after 15 seconds, you've pretty much opened up and changed all of one of the epoxides into it. When you open it up, it becomes an alcohol, and the other epoxide is still kind of unreacted. And so this kinetic resolution is where you essentially break one of the two enantiomers, and now they're no longer enantiomers of each other. You've turned one of those enantiomers into a totally separate compound. It's going to have different polarity. Wash it across a column, and 24 hours later, you've got separation of your enantiomers. You might ask, well, what do you do with the enzyme? And all you do is heat treat it. And so you can just heat it up, and the enzyme tends to die. Well, it's not a living thing. It tends to denature is what you call that. And that's when the enzyme just kind of unravels and it loses any of its ability to catalyze chemistry. There is another type of resolution. Your book doesn't discuss it, but it's based on this principle right here. Imagine that you wanted to separate a mixture of enantiomers, and what they do is they actually load the column up with chiral molecules. And so while the analogy is probably a little grotesque, imagine you had a big pile of hands and you wanted to separate those hands. If you've seen llamas with hats, you know what I'm talking about, then it might be a little funny to you. But if you have a big pile of hands and you want to separate those hands, the right hands and the left hands are chemically and physically the same because they're enantiomers of each other. And so you just fill your column up with only right-handed gloves. And I realize this analogy gets pretty ridiculous, but just stay with me. And so as the hands trickle down through the column, the right hands will get stalled by occasionally fitting into one of those right-handed gloves, and the left hands are going to move through the column more quickly because they're less likely to get trapped inside of a right-handed glove. And so your left hands will come off first, and then your right hands will come down later. So that's the idea of what they call chiral chromatography. It's a third type of technique. It's probably the one that is used in the laboratory most often, but it's not one that your book talks about because the book is kind of outdated on that. It's not up to date on that particular technique, or I didn't read it carefully enough to see that they did indeed mention chiral chromatography. So now we're ready to ask the question that hopefully has kind of rattled around inside of your head is, why only carbon? What about the other atoms? And so let's pull up ChemDraw and think about oxygen. Right? Well, the honk X rules for oxygen tell us that oxygen has a tendency to have two lone pairs and two bonds. And so either an oxygen can look like this, and you imagine this over here could be a methyl group, and this could be a hydrogen, and then you have an alcohol, or you could put maybe an ethyl group on this side and a propyl group on this side. Whoops, that's a phosphine group. We want a propyl group right there. And now you have an ether. Okay? In either of those two examples, the oxygen is sp3 hybridized, good, but it has two lone pairs. And so in order to be a chiral center, it has to have 4 different things coming off of it. And lone pairs count as a thing coming off of it, but this got 2 lone pairs, so it's the same. Hydrogen doesn't make a chiral center because it doesn't even hybridize, and it also only has 1 bond. So again, honk X, we want to eliminate all of those. Hydrogen is out because it makes 1 bond. Oxygen is out because it tends to have 2 lone pairs. Carbon is the one that we've been talking about, so hopefully you recognize that it can be a chiral compound. And now let's think about nitrogen. Well, typically speaking, nitrogen makes 3 bonds and has a lone pair. And as long as these 3 bonds are going to 3 different things, so we'll put a methyl group on this one, and we'll put an ethyl group on this one, and we'll put a hydrogen over here, then this meets all of the criteria that are typically associated with a chiral center. So then the question is, can nitrogen be a chiral center? And the answer is not really. And the reason for that is nitrogen has a tendency to invert. What it means is that this nitrogen here on the left-hand side is sp3 hybridized. This is a figure from your textbook. I don't remember which figure it is. It's after figure 4.12. The nitrogen here with these 4 different things on it is sp3 hybridized, but the energy barrier between nitrogen being sp3 hybridized and nitrogen being sp2 hybridized is very small. And an sp2 hybridized nitrogen is trigonal planar, where the methyl group and the ethyl group and the hydrogen are all in the same plane, and this lone pair actually exists in an unhybridized p orbital. This would be a p orbital right here. So this is kind of what an example of an sp2 hybridized nitrogen would look like. Send it back. And then we still can't see the nitrogen. Let's flip this thing around and maybe that'll allow us. Nope, that still isn't helpful at all. Okay, so the lone pair right here exists in this p orbital right here. And then the energy barrier between sp3, which is what this nitrogen started as, and sp2, which is what I'm showing you right now, is very small, meaning that it can hop up a little bit in energy to get to this sp2, and now it's not chiral. It's sp2 hybridized. That is against the rules of chirality. And when it drops back to an sp3 hybridized nitrogen, and the lone pair goes back to being well behaved, and then this thing kind of goes back, it doesn't remember if it was R or S originally. It has no memory. And so the nitrogen will tend to flip back and forth. It kind of flitters back and forth between R and S and R and S and R and S constantly at a rate that is so predictable that they actually have a clock that's based on the number of inversions per second that ammonia typically makes. So it's kind of like an umbrella that just flips in and out and in and out and in and out, and so it doesn't produce a reliable chiral center. So if you're asked to identify all the chiral centers in a compound, nitrogen does count as a chiral center, but it's a crappy chiral center because it's just going to flip. It's going to change its mind constantly. So if you spent your life trying to synthesize a chiral nitrogen, you would be wasting your life because that chiral nitrogen, the second you make it, it would flip over. Most likely it would flip back and forth so quickly that you wouldn't be able to isolate that. So we don't treat nitrogen as a useful chiral center. So why isn't nitrogen typically chiral? Well, I'd say why isn't it typically considered a useful chiral center is a better way of thinking about that one. And the answer is because it constantly inverts. Oxygen isn't typically chiral because it's got two lone pairs, and nitrogen isn't a useful chiral center because it's constantly inverting. As a side note, here's a phosphorus. Nitrogen and phosphorus are in the same column of the periodic table. And that means that they're going to have very similar properties. But as you move down the periodic table, what happens is the energy barrier between sp3 and sp2 starts to get much larger. So phosphorus will also invert its stereocenter, but it does it very slowly. And if you attach the phosphorus to these large, sterically bulky groups, they tend not to want to invert. It's just too much effort. And so they can this particular compound, you can isolate it, and as long as you keep the temperature low and don't expect it to last that long, it acts like a reasonably stable chiral center. Okay, that wraps up. There's no definitions for you. That's kind of a variety of topics dealing with chiral carbons and chirality in general.